Welcome to GriidAi. This is one of the platforms that has been developed with the noble intention where we try to reduce the time and the complexities that is being involved in engineering of the spatial data sets. But whereas the platform at the same time enables us to have a much detailed insights on the results or the analysis that we are carrying out. So that's the main vision and potential of this platform too. So now in today's experiment, we'll be starting on sea level rise. So let us start a chat session. Here you can see we can add multiple chat sessions, but currently this, let me rename it as sea level analysis. So whatever the data sets that is required for sea level rise analysis, let us start uploading, and all the data sets is only raster data sets that we are going to use today. So we are uploading the data sets. Yeah, so it's basically just the sanity check and just starts uploading, and you can see the message, the file is large, upload may take. So that's a information for us when we are uploading a very large files like 1 GB 2 GB files, so that we can be much patient uh, while the files are being uploaded. So as the files are uploading, let's explore what are the different files that we are going to use for this analysis. So you can see the three main files that we are going to use for this analysis are the dem file and IDW file of sea level rise and MHHW. So let me explain you what is the IDW file mainly about. So the IDW file is mainly having the information of the sea level rise for the different time periods, but currently we are chosen to do 2030 analysis for intermediate high scenario. So basically this IDW file has been developed from the gridded points that we got from NOAA, where they are adapted to SSP models. The SSP models varies from intermediate high, intermediate low, and high also. And there are low scenarios also. Basically, these are the different shared socio-economic pathways. So for each pathways, there are different measures that is being taken by the governments and the policies that has been adapted in the ground. So currently, we have assumed we are either in intermediate or intermediate high scenario. That's the most matching with the current sustainability initiatives and all those things that has been taken by globally all the governments. So on that pathway we have taken it for 2030 year, and we are trying to analyze what will be the sea level rise for the Hillsborough County in Florida. So that's the reason we have taken the gridded data and we have interpolated those points across the Florida, and we have taken only a small section from that full Florida dataset, and that is for Hillsborough County. We are doing it. And the second important dataset is the MHHW datasets. This MHHW dataset is basically mean higher water, which represents the highest of high water tide height during a day. So the way that dataset is being developed is NOAA has taken 19 years of data and taken the mean of all the high tides, and those mean values has been set as the MHHW, and we are using it for the analysis so that any infrastructures that is being constructed across the coastal boundaries or coastal regions, we ensure that the water doesn't intrude to those infrastructures if we have constructed above the mean higher water. So that's the very purpose of having the MHHW dataset in this analysis. And lastly, the most important dataset is the digital elevation model of the terrain. That is, we have it in the resolution of 3 meters, both horizontal and vertical. That's the resolution of the DEM data, and that's the reason it is having a file size of 1 GB, 1.4 GB, and it's taking time to load. Of course, the system is very fast and it's already reached 91%, so probably in another few seconds it would finish the upload process. Yeah, as said, it has finished it fast. It has totally taken 4 minutes to upload all the files. Now if you go to the data catalog, you can see all the files have been loaded, and for rasters the files are symbolized by this square with a pink color. Right. Of course the vector will have a green, so you can easily differentiate between the rasters and the vector files. Now let's start analyzing. As a part of the analysis, the first initiative is to take up mean high air water and add it with the IDW values that we have interpolated for 2030 intermediate high scenario, so that we create a sea level rise surface for 2030 intermediate high scenario. So here you could see that the GriidAi started thinking. Probably it's assessing all the data sets, metadata, and all those things, and it's going to give a clear plan for me how it is going to process. So that's where it is thinking. Sometimes the beauty of this thing is now if you see, it has given a clear path. What's the plan and what are the files that it is going to take up and what sort of a band it is. What is a float? Is it a float 32 or what sort of a data category it is? And what is a projection system also that is being having in the data sets it is clearly given us. So, and finally it gives the steps that it's going to do, reprojects the resample and all those things, whatever it has to be done. And finally it gives us the edge cases also, where rarely such cases would happen, but it is giving a clear plan for that also. And finally it's asking me whether the output is that has to be created as a sea level rise surface for 2030. Yes. So now once I give the yes please go ahead, it's thinking at the back end and writing the code that has to be developed for such a data set, and in fact it has written and it's started executing the process also. So it's at very good speed. And here you can see it even shows the 5%. It has completed the analysis and it is showing working on it. Now it has gone to 15. Yeah. So the analysis has been finished and it is giving a clear things on what sort of a data it has created and what is the dimensions, data type, what is the no data that it has been represented. All those um, metadata sort of informations we are getting it from this, and you can see the file here also. And now if you wanted to visually see the file overlaid in the ground, yeah. So here you could see IDW files and the MHSW files has been added, and we are having the final raster of it. Now the next work is to subtract it from the DEM data so that we get the final inundation depth data. What would be the inundation depth of all the wherever the sea level rise is going to happen by 2030. So let us close this map. Now we are subtracting the sea level rise surface from the DEM so that whatever is left over in that rasters, basically whatever the negative values that are present in the rasters, it's going to be the areas that are going to be inundated, and all the positive values are going to be marked as no data. Yeah, so if you go through the plan, it's clearly understood the prompt that I had given, and it has given it in the steps and it's going to follow it. So that's the expected output that I wanted. So it has computed the final results also here, and the data set has been loaded in the data catalog. Let us see it in the map. Yeah, so the operation that we requested is wherever the minus 99,000 is present, it should be marked as the value of 2. So you can see the pixel values. All these white regions are being marked as 2 because these are the regions which were having minus 99,000. Basically this 99,000 is present in the DEM data to indicate wherever the sea level sea water is present. So that's the reason we have marked it as minus 99, and other regions we have retained it as it is, whatever the pixel values are present, we are retaining it. And if any of the pixels are having the values above 0, it has been marked as a no data because we are subtracting sea level rise from the dim data. And so any pixels having values more than the sea level rise surface plane, it's going to be a non-inherited area. So that's why we initially marked it as a no data itself, as we are not going to use any of those values in the future. Only the values that are below a sea level rise surface plane is going to be considered as the inherited areas, and these are all the inherited areas that we are having. Now the next objective is to classify all these data sets into 2 to 3 categories. So in order to do that, the objective is to create two distinct rasters or two distinct values in this raster, that is pixels with the value of 1 and pixels with the value of 2. So the 2 is already being generated. Now the pixels with the value of 1 we need to generate, that is basically the areas that are inherited in the land areas. So let us initiate that operation. So see, now it has clearly given a plan. For each pixel it's going to take up and check whether the value is 2. If the value is 2, then it is going to retain it as it is, and if the pixel value is less than 0, it's going to mark it as 1, and if the pixels are 0 with the value of 0 itself, then it's going to mark it as no data, because 0 is something, there is no inundation that is happening at that area. So why to retain those pixels too? So that's the reason we are marking them as a 0. That is a known data, and now our final rasters would be having only two values, either 1 or either 2. So wherever 2 is present, it's going to represent the sea water, and 1 is representing the areas wherever the areas that is inundated because of the sea level rise. So that's a good binary raster that we are going to generate, which would help us in easily identifying the areas. But unfortunately, you could see the LLM has taken the wrong name, so we'll correct that wrong name for the output rasters. Now even the reclassified raster is generated. Now we can go and see the reclassified raster also. So see, now the raster will have only the values of either 2 or 1. So now as this analysis has been done, now comes the importance of the water file that we are having for the Elsbar County. So this is the file that we need to use. So in order to mask all the water bodies that are present in the inland, so basically you can see the water bodies are, some of the water bodies areas are also having the pixels. So all this water body will be counted as SLR annotated, but in the reality they are already a water body, and marking them as extra annotated is wrong. That's where the false positive increases. So that's the very reason we decided it's important to mask all these water bodies, whatever is present in this area. So now let us do the masking also. And it is, by the way, the most important step is to do the propagation and see how the water would propagate from the ocean to all these regions. So even before marking out all these water bodies as masked and all those things, it is important to understand how the sea level rise or the sea level water would be intruding into these inland areas. So now the simple logic that we are going to adapt is wherever the pixels of value of 1 is closely connected to the pixels of 2, that is the sea level water, all those areas are going to be impacted because of the sea level rise by 2030. So in order to do that, there is this process called propagation, which is a eight directional analysis, where it starts searching each and every pixels whether it is connected to the pixel value of 2, and if it is connected to the pixel 2, it marks those pixels as a inundated areas. So this needs a detailed prompt. In order to save the time, I had already written the prompt and kept it ready so that I can save some time in this video. So here you can see we are specifically requesting a 8 directional Mori neighborhood method, which is going to look for all the pixels around the pixel value of 2, and if it is connected to 2, then it's going to mark it as 3. And all those analyses are clearly given here, what sort of a model, libraries that has to be used. So the beauty of the platform is it's able to understand all these things. It takes the required libraries, installs, process it, and gives your output. There's no headache for us to worry about all this installation of the libraries, where to install, what to install, all those things. So see, it is clearly given the plan and what it is going to do. So the other advantage of this platform is that sometimes when it has written the code and it has analyzed itself that this process is going to take much time, it gives a hint to us that it's going to take much time, so we can come back afterwards. So in meantime we can go back to our other works and we can return here and see the results also. So it has created all this three different layers that we term it as a true SLR and low-lying extent and hydromask. So the hydromask is basically the pixels with the value of 2. We need not very much about this one. And the regions where low-lying extent is being marked, they are having the value of 1, basically representing that the regions are not directly connected to the oceans. But as per the SLR surface plane, those regions are falling below that. So that's the reason we are marking it as low-lying regions. And the most important part is the true SLR extent, where they are having the pixel value of the next step is to mask all the water bodies in order to avoid the false positives by masking them. So in order to do that, we'll be doing it on the classified raster. So it has understood the requirements wherever the pixels of FL Ilspar water is having the value of 1, it's going to set an output of no data, and the main raster, that is the propagated classified single raster. If there is no pixel value of 1 in the water raster, then it's going to mark it as a then it's not going to mark any modifications in this raster. Now if you could see this raster, it has clearly masked out all the water regions so that we don't have any positive false positive values. in these areas. So these areas will not be added up to that it is a low-lying area or true SLR regions. That's the reason we masked out all these regions. Now we can separate all these rasters into 3 different rasters. Now it is separated and brought as a 3 different rasters, that is true SLR regions, low-lying areas and hydromask. Now we can see the true SLR regions. So now it has clearly identified the areas, and these areas are the true inundation areas that is going to happen, that is going to get inundated due to the sea level rise. And in the same way we have the low-lying areas too. Yeah. So the next step is, again, we need to mask some more water bodies, because of the water body edges also has to be masked out, which is basically these water bodies we have been able to identify. The water body edges keeps varying because of the seasonal characters in the region. During the summer the water body edges will be less, and when it is rainy season or winter, the water body expands, the circumference of the water body expands. So we have even identified the water body perimeter areas, and we have identified the pixel regions wherever it is present. So now we are going to mask them also into this rasters. Now it has given the final masked raster layers for both true SLR and low-lying areas. Now comes the, in order to extract the depth for these regions, And in order to use it in the platform or any other vector file, any other softwares, it would be better if we have the vector files. So that's where we are initiating a process for vectorization of this rasters, these two rasters. And most commonly used projection is 4326. So we have asked two operations, one is vectorization as well as in reprojecting it to 4326. So it has clearly identified that, or it has clearly understood the process. So now you could see that it has converted all the pixels to the vector format. It has been efficiently doing that vectorization too. So we have finally got the vector files also. So the last step is to now take the depth data also for the extents that we have created. As we did for the true SLR, now we'll do it for the low-lying areas also, so that we can have the depth of inundation for both the different categories. In meantime, let us see how the water depth for the true SLR regions have come out. Yes. So now you can easily see all these regions and what is the depth of water level that would be at that region. So it will be 120 millimeters at that areas. So that's a clear identification of all the true SLR areas that is going to be inundated because of the sea level rise. And I think possibly we'll be having, yeah, we are having the low-lying areas also identified now. So all these are low-lying areas, and the corresponding inundation depth pixels are also clearly there. So it's all 85 millimeters. Is very shallow inundations is possible. So on this whole exercise, we have been able to identify the different types of SLRs categories, that is true SLR and low-lying areas, for the time period of 2030 intermediate high scenario. Now, if we are able to generate IDWs for different time periods and scenarios, the same method or same approach can be applied, and we can see how the sea is intruding into the land regions due to the climate factors. So the whole objective of this experiment was to see how the sea level rises radiating over the land regions. And by the end of this experiment, we have been able to visualize and see the areas where the water has intruded and easily demarcate them. So that's the beauty of the platform, where we have not even written single code till now, but we have been doing the most complex sea level rise analysis for this whole region. So that's the advantage of this platform.